everyone. I'm Adnan Abdullah, graduate as mechatronics engineering and pursuing my master's at the American University of Beirut. So this presentation will be dedicated to present the project that I did for the system analysis and design course, which is designing, modeling, and implementing a 2D manipulator and controller. All these steps were done using MATLAB and Simulink. The next step was uh, deploying the built model on Simulink to the real hardware. So as we can see, this is the hardware that I built from using 3D printing. I manufactured a 2DOF arm and I implemented the circuit. I assembled it and starting by modeling the dynamic equation. As we can see, we have the dynamic equation. Then we linearize this dynamics to deal with linear system. We used Simulink to implement an LQR controller along with feed-forward term. We will see in details each term. So this is the robot model modeled by this equation. This is the feedback linearization or feed that was used as feed-forward term to compute the required torque for our plant. And this is the equation used to model the feedback linearization block. Finally, this is the total system where we created a deviation model that takes into consideration or computes the error between the desired position and current position, along with the error between the desired and current velocity, feeds them to the controller. For example, the LQR that computes acceleration. The acceleration is fed to the feedback linearization block that computes the torque, and finally, the plant takes the torque and generates the required position by integrating twice the acceleration. This slide shows the usage of Kalman filter, where we simulated our encoder by adding noise and estimating the response. And these are the results obtained from Simulink. We have in blue the simulated encoder. We have the estimated measurement or estimated states in red and the actual position in yellow. I should mention also that we designed a trajectory planning algorithm to minimize the error between each step and obtain a smooth trajectory. Then we incorporated the actuator dynamics into our model, and finally we simulated on real hardware. So as we can see, we were able to build the full system. I should mention also that another method was employed for linearizing our system, which is the computed torque method, where a controller was implemented for each joint. This is in brief the block diagram, and this is Simulink implementation, where each block was implemented using Simulink. This is simulation. As we can see, we have the desired trajectory. We have the error model that, as I mentioned, it computes the error E1, E2, E1 dot, and E2 dot, feeds them to our LQR controller, which is U equal minus KX, and X are the state vector, E and E dot, takes them to the feedback linearization, which is the equation of motion inverted, computes the required torque, feeds them to our robot to compute the required acceleration, integrate twice acceleration to obtain the desired position, and finally, this is a Kalman filter with the estimation and the sensor simulation. As we can see, this is the obtained tracking, where we have tracking for the first joint, second joint, tracking for the first joint, and the required the obtained torque. As we can see, 0.2 Newton meter as a maximum value, and this is a reasonable value since our links are of a few grams and they are 3D printed. So that's it mainly. I hope that you enjoyed this presentation and looking forward for the next step and upcoming projects. Thank you.